Hey, math peeps. So today we want to focus on solving. Now, I lump solving radical and rational equations together in one because of the similarity of our methodology and what we have to do, okay? So if you're with me in a regular class from our school, you will be doing this all in one day. If you are watching me from a different school or from a slightly different program, you may do these two things in 2 different days. That's okay. We're going to take care of it all in one lesson here, okay? Okay, so solving radical and rational equations. This is lesson 5 in my order at regular school. So one of the things you'll like about, or maybe you'll like, I don't know, in 20-1, you focused a lot on solving rationals and solving radicals, but you did it algebraically. In 30-1, the outcome is really just based more on using your graphing calculator and understanding how to manipulate and look at equations and functions through your graphing calculator and grab this information from there. Okay, but we will do a quick review of how to solve algebraically, just to freshen your mind. So I'm going to take 2 equals the root of x plus 1. I'm going to solve that algebraically. So I want to get rid of the radical. I'll do that by squaring both sides. So that'll be 4 equals x plus 1. And then I will bring that 1 over and I have x is 3. Now with radical graphs, you do have to check them to make sure you didn't find an extraneous solution. An extraneous solution is one where the math actually tells you that's the answer, but that doesn't actually exist. And so the only way to check for that, the only way to account for that is we just plug it back into the original equation and make sure we get a true statement. That's called a verification. And we're going to do lots of verifications when it comes time to handle trig together. Okay. So here I go. I'm going to check it and I'm going to go 2 equals the root of 3 plus 1. The root of 3 plus 1 is 2. So 2 equals 2. In any sort of a verification, you always want to work down. You want to keep the left and the right separate of each other and work down until you see that they come to the same number. That's how you verify something, okay? So the solution set is x is, in this one, it's only one solution, but we put it in set notation, brackets, and that would be 3, okay? Okay, a little trickier. We have the root of 3x squared minus 5 equals x plus 4. Again, I want to get rid of the radical, so I would square both sides. That would give me 3x squared minus 5 on the left side, but you got to be careful with the right. I get x plus 4 all squared on the right, so that's x squared plus 8x plus 16, right? It's x plus 4 times x plus 4. Square the first, double the product, square the last. You'll remember that from our 20-1 moments together, if you were with me in 20-1. Okay. Now I want to bring everything over to one side and I want to try and factor it or use the quadratic formula if I can't factor it, okay? So 3x squared, I'm going to bring that other x squared over, so that'll be 2x squared. My 8x comes over, so that'll be negative 8x. And my 16 comes over with the negative 5, so that'll be negative 21. So I'm looking at 2x squared minus 8x minus 21 equals 0. If this was factorable, I'd be looking for 2 numbers that multiply together to give me negative 42, 2 times negative 21, and add together to give me negative 8. If I go through the factors of 42, none of those are going to give me the negative 8 that I want, which sends me to the quadratic formula. Okay, so x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Plug in 2 for a, negative 8 for b, and negative 21 for C. Okay, rounding to 2 decimal places here, that's going to give me x is 5.8, sorry, 1 decimal place. That's going to give me x equals 5.8 and x equals negative 1.8. Okay, I still do need to check these. Now you got to be careful if you use a rounded version, and don't ever use a rounded version unless the question says you can use a rounded version. Technically, I didn't say in this guy, round your answer to the nearest 10th. So technically, I should have left things at 8 plus or minus the root of 232 over 4 and then simplify 232, right? I can take a perfect square factor out of root 232. I'll actually tell you the simplified version of root 232 is 2 root 58, okay? Anyway, this is just a quick review, and that's why I'm not going there. I'm just going to go with the decimal approximations. But with the decimal approximations, if you go to plug them back in, you're not going to get an exact answer because you weren't using the exact answer, right? So you'll get something like, you know, you might get something like 3.999 equals 4.001 or something like that. You can assume that that's probably okay based on the fact that you used a rounded version, okay? So if I go to check it, I do end up okay, 9.8 is 9.8, and 2.2 equals 2.2. So it worked to the nearest tenth for this guy, okay? So that's a quick review of how to do it algebraically. Now we're going to take a look at it graphically. Just to finish this off, the approximate solution set then would be x equals negative 1.8 and 5.8. Okay, so now we're going to take a look at conceptually what we're doing from a graphing standpoint. So consider the graph of the function y equals the root of x plus 1 below. And you should be comfortable looking at that and saying, yep, that is for sure the root of x plus 1, because I know what the root of x looks like, and I know that if I replaced x with x plus 1, that is a horizontal translation left one. So it makes total sense that this one starts at -1 now instead of 0, 0. Okay. Determine the roots algebraically. Well, if I was going to determine the roots algebraically, I would set y equal to 0. I would end up having to square both sides. So that's 0 equals x plus 1, and then bring the 1 over. So I'd have -1 equals x. Using the graph, state the x-intercept of y equals the root of x plus 1. Well, I can see that that -1 comes 0. Okay. So the x-intercepts and the roots are the same thing here. Describe the connection between the roots of an equation and the x-intercepts of the graph. I just said that. They're the same. Okay, state the solutions to 2 equals the root of x plus 1 using your graph. So if I'm looking at 2 equals the root of x plus 1, really what I want to do there, I'm just getting a straight line for you. I'm looking at that. Okay, so using my graph, it looks like it would be at 3. Okay, now remember, when we're reading these things from a graphical standpoint, I only actually care about the x value. There was no y value in this equation. The equation was 2 equals the root of x plus 1. So my solution will always be the x value at the point of intersection. Okay, so in this case, it'd be x equals 3. Sorry, I tried to advance and I forgot that my ink was still on instead of my mouse. Don't worry about that green line just yet. There, so we have x equals 3, okay? Now, using your graphing calculator, state the root of 2 minus the root of x plus 1 equals 0, okay? So now, if I graphed 2 minus the root of x plus 1, I'm going to get this purple graph that has appeared here. You can follow it with my mouse, okay? And I can see that when it equals 0, that's also 3. Okay, well, what am I trying to do? What's the point I'm trying to make? I'll tell you the point I'm trying to make. This, equals 0, okay, I don't like it when it switches lines like that, is just a derivation of this, right? All I really did was I took that 2 equals the root of x plus 1, and I subtracted the root of x plus 1 from both sides. That gave me 2 minus the root of x plus 1 equals 0. So I manipulated the formula, but it doesn't change the answer. The answer still ends up, sorry, the answer still ends up being that x equals 3, okay? So part of our goal in this with 30-1 is to be okay manipulating equations and still understanding what our answer is and what our answer means, okay? Okay, let me get this ink off. Create another equation that could be used to determine the solution to y equals 2 and y equals the root of x plus 1. So we did, we moved everything over, like we moved the root of x plus 1 over. I could have also just moved the 2 over, right? So I could have -2 plus the root of x plus 1. That would have been totally fine, or the root of x plus 1 minus 2. Okay, same thing. That also would have worked. Okay, what would happen if you were asked to find the solution to 2x plus 3 equals the root of x plus 1? Now, if you were wondering why that random green line appeared a few slides ago, the random green line is the equation to 2x plus 3. If I'm looking for 2x plus 3 equals the root of x plus 1, I'm looking for the intersection between the green line and the blue line on my graph. And you will notice there is no intersection between those, so there is no solution, okay? There is no solution because there is no intersection point. Okay, a student decided to solve the system. Y1 is x plus 2 root of x minus 7, and y2 is 4, and she was going to do it graphically. So she used the following equations of lines. I'm going to scoot right down to the bottom so I know what I'm being asked. The equations that she could use to correctly solve the system. So I've given you 5 different possibilities. I want to know which ones would work. Okay, so in the first one, she went y1 equals x plus 2 root of x minus 7 and y2 equals 4. That's essentially what the question was asking in the first place. That works no problem. In the second one, she went y1 is 4 and y2 is x plus 2 root of x minus 7. That is also okay. It does not matter which one you're calling y1 and which one you're calling y2. That is completely inconsequential. In the third one, she went 4 minus x minus 2 root x minus 7 and y2 equals 0. Well, that would work if these guys were equal to each other and then she brought the x over and she brought the 2 root x minus 7 over. That would leave her with 0. So that one is also totally cool. In the fourth one, she went x plus 2 roots x plus 2 root of x minus 7 minus 4. So then what did she do? She left these guys where they were and she brought that 4 over to be negative 4. So that's totally okay. And then in the last one, she has 4 minus x plus 2 root x minus 7 with y2 equals 0. That one is not cool to me. And here's why. If there's a negative x here, that means she started with that 4, she brought the x over, so that would be negative x, that's cool. But then she would have had to bring that guy over, so that guy also should have been negative, and it's positive right now. So he does not work. 5 is the only one that she couldn't have used to correctly solve that system. Okay, so this is a great example of a way where they want you to be cognizant of how to manipulate the equations and know that it will still get you to the answer that you want. Okay. All right. Awesome. So it's 1, 2, 3, and 4. So a summary of radical solving. That's radical solving, man. Sorry, I couldn't resist. Okay, you can only solve radical equations algebraically or graphically, or you can solve radical equations algebraically or graphically, but you're only going to be asked in 30-1 to do so graphically. When solving for an equation that is equal to 0, you're searching for the x-intercepts or the zeros or the roots. When solving for 2 equations, you're looking, or when solving using 2 equations or for 2 equations, you are searching for the x value at the point of intersection. Don't get caught in telling me that it's a coordinate pair. It's not a coordinate pair here, because it's not technically a system, right? So you're just looking at the x value of the point of intersection, okay? All right, now we're gonna switch our focus to rationals, and it's a very similar conversation. That's why I've lumped them together in one video. Okay, so first thing we're gonna do is review how to solve algebraically. So usually when we're solving these guys algebraically, we wanna first state our NPVs. We know that x can't equal 1. And then we want to get rid of the fraction, okay? So I'm just going to multiply every term by x minus 1. That will get rid of my denominator of x minus 1. So that's going to give me 2 times x minus 1, minus x plus 3, because my x minus 1's divided each other out, plus 1 times x minus 1 equals 0. So now I just need to solve this fella. 2x times x is 2x squared, minus 2x, minus x minus 3, and plus x minus 1. Combine like terms, I'm looking at 2x squared let's see here. I got negative 2x and negative 4 equals 0. Divide by 2, x squared minus x minus 2 equals 0. And let's see if I can factor that. Two numbers that multiply together to give me negative 2, add together to give me negative 1. That would be negative 2 and 1. So my solutions are x equals 2 and x equals negative 1. Now, with rational graphs or rational functions, you don't have to plug them back in and verify. You just have to make sure you didn't hit an NPV. In this case, my NPV was x equals 1. So this isn't, neither of these are an NPV, so I'm good to go with both of them. Two solutions, x equals negative 1 and x equals 2. Okay, a little trickier on this guy. First, though, I'm going to state my NPVs, which is x can't equal 0 and x can't equal 1. Then I'm looking at multiplying everything by the common denominator to wipe out the fraction. So the common denominator would be x times x minus 1. So essentially, I'm going to take this guy and multiply by x times x minus 1. I'm going to take this guy and multiply by x times x minus 1. And I'm going to take this guy and multiply by, you guessed it, x times x minus 1. Okay, now when I do that, I'm just going to switch color here so you can see. For the first guy, my x minus 1s divide each other out, so I'll be left with x times x, which is x squared. In the second guy, my x minus 1s divide each other out, and I'll be left with 1 times x, which is x. And then in the last guy, the x's will divide each other out, so I'm left with 2 times x minus 1. Okay, and that's what you see here. So x squared equals x plus 2x minus 2. Bring everything over to one side. So this is x squared minus 3x minus 2. Sorry, plus 2 because my minus 2 comes over. Two numbers that multiply together to give me positive 2 and add together to give me negative 3. That would be 1 and 2, or negative 1 and negative 2, sorry. So x minus 1 and x minus 2, which means x equals 1 and 2. Again, I got to check that on my non-permissible values. X can't equal 1, so this guy is no good. And my only solution, my only valid solution would be x equals 2. When you're doing these things, we do need to see that you had 2 solutions stated and that you realized one of the solutions doesn't work. So scratch it off, call it extraneous, do whatever you want, but you need to communicate, hey, that's a bogus guy. He's out of the equation. My answer is just x equals 2, okay? All right, now our focus on solving rational equations will be graphically. So as in radical and other equations, we will search for the x-intercepts or 0 when one side of our equation is equal to 0, or we search for the point of intersection when graphing 2 functions, but I want you to be even more clear with that statement. It's not just the point of intersection, it's the x value at that point of intersection, okay? It's the x value of the point of intersection. Okay, for the following rational function, determine the equation of the asymptotes, the domain and range, and the 0 of the function, okay? So I can see I have a vertical asymptote at x equals negative 2. I have a horizontal asymptote at y equals negative 4. My domain then would be x is a member of the reals, but it can't be negative 2. And my range would be y is a member of the reals, but it can't be negative 4. Make sure you're labeling domain and range. Like actually write the word domain and write the word range, okay? And then for the x-intercept, we can see it right here. It is close to negative 2, maybe negative 1.8, negative 1.75 in this case, okay? All right, next up. Given the graph y equals 2x over x minus 1, determine the solution to 2x over x minus 1 equals 1. Okay, now I've given you the graph, but just if you want to try this on your graphing calculator, the other conversation I just want to have around this is just be careful how you're doing it. If you have a newer Casio or a newer TI, you want to open up the fraction first so that you can write 2x on top and x minus 1 on the bottom. Okay, on a Casio, that's just as easy as pressing your ABC button, or your on the newer Casios, it looks like a box over a box. It looks like It's right underneath your variable button, but it looks like this. This is actually the button. Okay, that's the button. And then on a newer TI, you would press alpha y equals 1. On an older Casio or an older TI, and when I say older Casio, I also mean just the white Casios, right? The 9750 GIIs are the white or pink ones. They're what we would call the older model. And then the 9750 GIII is the black one. That would be the newer model, okay? So if you have an older Casio or an older TI, what you want to do there is you just want to write it as a division statement. You just have to remember that the denominator has to go in its own set of brackets. So you're going to go 2x divide by bracket x minus 1 bracket. Okay, so that's what would go in y1, and then 1 would go into y2. And you should get an intersection right here, which is at -1. Okay, at -1. I'm just reading that off the picture you were given, but I think it's important that we have that conversation about how to input it in your calculator as well. Okay, awesome. Okay, given the graph of y equals 1 over x squared minus 1, determine the solution to 1 over x squared minus 1 equals 1. Again, if you want to practice graphing this on your graphing calculator, the same sort of conversation applies. If we want to read this off of our graph right now, we're here and here. I would actually like you to put this in your graphing calculator for a second so that we can get a decent answer. We're not just guessing here. Like, you know, it looks like it's around 1.4, negative 1.4, maybe 1.5, but I'm guessing, right? So it'd be better to stick that in your calculator, calculate that point of intersection. On a Casio, you do that by pressing F5, F5, G-solve intersect. And on a TI, you would have to go second trace 5, enter, enter, enter. Okay. And you should get negative 1.4 and 1.4 when rounded to the nearest tenth, like the question asked us to. Okay. All right, determine the roots. 2, x plus 6 over x plus 2 minus 5 equals 0. So we're going to throw this in our graphing calculator. You should be pausing me and trying this and then comparing your picture to my picture. My picture looks like this. Now, there is another section to this graph. I just never bothered I never bothered adjusting my window setting to show you both sections of the graph because this is where the x-intercepts lie, and that's what I was after, okay? So I just made my picture to show the two x-intercepts, which look to be at -1 and 4. But just because it looks like that doesn't mean it is that. So you do want to actually calculate it and make sure that you are getting the correct answer. Like for this, it would really suck if, you know, that 4 was really, you know, 3.79 and you just thought it was 4, right? So use your graphing calculator to ensure that you actually have an accurate result. But it is at -1 and 4. Okay. All right. Solve x squared minus 3x minus 7 over 3 minus 2x equals x minus 1. And we're going to answer that to the nearest hundredth. So pause me and make sure you can get the right picture. Here's the picture you should have. So again, I have two intersection points here and here. Okay, again, on a Casio F5, F5, it's going to take you to the one on the left, and then you just right-click your way over. On a TI, you'll have to do it twice. Make sure your cursor is close to the one you want, and then go second trace 5, enter, 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 and then do it again. Okay, and you should get -0.43 and 3.10 when rounded to the nearest hundredth. Cool. Okay, just a little warning. When solving rational equations graphically, leave the fraction as it's written. Do not multiply by a common denominator here. Why not? If you multiply by a common denominator, you wipe out the fraction. And if you wipe out the fraction, you may actually get an answer that was once a non-permissible value, right? Remember when we did it algebraically, we wiped out the fractions, but then we had to make sure our answers weren't a non-permissible value. We did that kind of check and balance. If you were just to multiply by the denominator here, there is no check and balance there, and you may actually be stating an answer that's actually extraneous, okay? So you may end up getting rid of a possible non-permissible value. Okay, the intensity I of light in watts per square meter, W per meter squared, at distance D. Okay, it's at this point where most of you have shut down because you're looking at this and there's too many words with too many letters, okay? You have to push yourself through that. This is not a complicated question. It's just you have to get the information that you need, okay? So if you just shut down, I want you to rewind here and start again and force yourself not to shut down, okay? Okay, so I'm even gonna start the question again for you. The intensity I of light in watts per square meter at a distance D in meters from the point source is given by this formula. Okay, they gave you a formula. I equals P over 4 pi D squared. P is the average power of the source, and we know what I is and we know what D is. Now, how far away from a 500 watt light source, okay, is an intensity of 5 watts per meter squared? So my 500 watt light source is my average power, so that's my P. My 5 watts per meter squared, that's the intensity, so that's my I. And I'm looking for how far away, well, that's my D, okay? So I'm looking at an equation right now that says 5 equals 500 over 4 pi D squared. So I went ahead and graphed that in Y1 and Y2, okay? And you will see my graph here of my Y1, which is the blue, and the Y2 is the green. You'll also notice that I'm ignoring this guy over here. There is obviously an intersection point around there. I am ignoring it right now because I'm talking about distance, and distance isn't negative, okay? So although there is an answer there, it doesn't exist in the context of this question, and so I'm not paying attention to it. I'm only gonna pay attention to the positive one, okay? F5, F5 if you're a child of Casio. Second trace 5, enter, enter, enter if you're a child of TI, and you should get an X value of 2.8. Here's a classic example of what I was talking about earlier. Don't just guess and say, oh yeah, it looks like it's around 3. You have to make sure you calculate it, okay? All right, so the intensity is 2.8 meters away from the light source. Okay, great. All right, a student wishes to solve the equation x over x minus 1 plus x equals 2 graphically. Determine 3 ways a student may enter this into their calculator and receive a correct solution. So I want to know what they're going to enter, and I want to know what sort of solution they're going after, okay? There are many, many ways we could do this. You jot down a couple of thoughts, pause me and jot down a couple of thoughts, and then I'll show you mine. So here's the first one I did. I said, hey, let's put into Y1 x over x minus 1 plus x, and into Y2 put 2, and then I'm looking for the x value of the point of intersection. Okay, so that's one way I could do it. Another way I could do it is I could say, hey, let's put x over x minus 1 plus x minus 2 all in Y1, and then in Y2, that would leave us with nothing. So in Y2, I'll put 0, and then I'll find the x value of that point of intersection. So I just manipulated the equations around. Totally fine. Okay, that will also get me to the right answer. Or I could have said, hey, if I'm going to bring everything over to one side, I don't even need a system anymore. I could just bring everything over one side, and I could look for the x-intercepts, okay? Because the x-intercepts are where y equals 0. True. So that's another way I could do it. So there's 3 different ways I could take the same question, manipulate it differently, and arrive at the correct answer, okay? All right, so let's summarize that now. Finding the roots of a rational function is the same as finding the x-intercepts or finding the zeros of a graph. When graphing 2 functions, the solution is the x value at the point or points of intersection of the graph, okay? There are always several ways to manipulate the equation to determine the solution. All right, so I've got your homework here. This is your mission should you choose to accept it, and you have to. Make sure you connect with me if you do have any questions. Make sure you're taking the time to communicate clearly and concisely. Remember, it's all about the communication. And have a fantastic day. I will see you soon, hopefully, for the next lesson. Take care, guys.